be the critical value of x, and y be the critical value of y. So at the critical point, what is dz? If you satisfy the first order conditions, what is f sub x? What is f sub y? 0. So that means at this critical point, this is 0 for all possible values of dx and dy. Because if f sub x is 0, f sub y is 0, then that total differential is 0 for all possible values of dx and dy. So let's note that. Next, let's talk about the second order total differential. The second order total differential is written this way. The second order total differential. This is the first order total differential, just oftentimes called the total differential. Okay. And if you take the total differential of the total differential, you get the second order total differential. So this is just this. And what is dz? Let's substitute in for what dz is. This is the total differential of this. So it's the change in the change in the z. It's like a second order, like the second order. Okay. And we're taking the total differential of this expression right here. But notice, let me write this out. F sub x is a function of x and y. So let me just emphasize that. F sub y itself is a function of x and y. So we're taking the total differential of this expression right here. Now, we just use the same rules we used before. If you want the total differential of this whole expression, let's break it down part by part. Let's get the total differential of this part right here. What is that? Well, the total differential of this part right here is just the partial derivative of f sub x with respect to x. Take the partial derivative of this with respect to x, multiply it times the dx. But it's already multiplied by the dx here, so you've got 2 dx's here. Then this f sub x could change because of the change in y. So you'll have a partial fx, partial y, times the dy, times the dx that's already out here. Oh, I lost you. All we're doing is taking the total differential of this expression right here. We're treating dx as if it were just a constant. But f sub x is going to change with x and y. So we're just taking the total differential of this term and it is that. If we take the total differential of this second term here, it will be this. It will be partial fy, partial x dx times dy. It's already there. Plus partial fy, partial y times dy times the dy that's already there. So that is what this is all just the second order total differential of z. And I can rewrite it now this way. Partial fx, partial x is just f sub xx. This is dx squared. this term right here is just f sub yx times the dy dx. This term right here is f sub xy dx dy. And this last term is f sub yy times dy squared. And there's one more thing we could do to simplify this. Notice, by Young's theorem, what is true about this and this?
They're the same.
They're the same. So let's just call it f sub xy. And notice this is dy dx, this is dx dy, but they're the same. So we can simplify this to this. The second order total differential, we're done now. It's just this. F sub xx times dx squared plus 2 f sub xy times dx dy plus f sub yy times dy squared. That's the second order total differential. And that tells you the change in the change in z. Whether the change in z is getting bigger, for example, or smaller. Now, this second order total differential is a quadratic form in dx and dy. Let me write this again. Let's use our earlier notation. Q equals a u squared plus 2agv plus bv squared. And right below it, let's write our expression for the second order total differential. And you see, rather than Q here, we have this second order total differential. A, just think of A as being f sub xx. Now, A is thought to be a parameter, but so is f sub xx if you evaluate f sub xx at the critical values of x and y. F sub xx will just be some number. And it'll be comparable to A. Now, u is a variable, and so is dx here. We're thinking of dx as being a variable. So u is equal to dx. And rather than h here, you have f sub xy. And if you evaluate f sub xy at the critical value of x and y, that'll just be a number just like h is. The dx is u, dy is v. And those are considered variables. B corresponds to this, and v is just the same as y. Now, let me show you in a picture what's going on. Suppose you've identified a critical value of x and y, where the first order conditions are satisfied. And you're at this point right here. Here's x sub 0. Here's y sub 0. At this point, this critical point, f sub x is 0, f sub y is 0. And imagine you're thinking about this. You know at this point right here, what is dz, the first order total differential? 0. Imagine now you think about moving away from this point. If you move away in this direction, notice dx is positive and dy is positive. If you move anywhere in this quadrant right here, okay, you're increasing x and you're increasing y. If you move in this direction here, then you can see that dy is negative, but dx is positive. If you move in this quadrant, what's happening? X is getting smaller, but y is getting bigger. And if you move anywhere in this quadrant right here, your value of dx is negative, and so is your value of dy. So imagine you're moving away from this critical point, and for all possible values of dx and dy, there's an infinite number of paths you can take. So you want to know if for all possible values of dx and dy, suppose that second order total differential is positive. Then that means you have a minimum there. Because you know that dz is 0 at the critical value. You move away, and then dz is becoming bigger. Bigger than 0 means going up. No matter which direction you go, you're going up. So this point right here has to be a minimum. Because the second order total differential is positive for all possible values of dx and dy. So it's 0 here, you move away from it just slightly, and the value of dz has to go from 0 to something positive. So you're going up. It's 0 here, then it becomes positive. No matter which direction you go, dz is going from something that was 0 to something positive. So the value of z is increasing, no matter which direction you go. This is very clever. This is extremely clever. It's figuring out, because there are an infinite number of values for dx and dy. An infinite number of paths you could take away from this critical point. You have to show that no matter which of these infinite paths you could possibly take, doesn't matter. The value of dz is going from 0 to something positive. So, what is the condition for this quadratic form to be positive definite? Here's our a. You want that to be greater than 0. And you also want ab, and b is fyy. You want fxx times fyy to be greater than h squared. So there you have it. The second order total differential is a quadratic form in dx and dy. So this will be positive definite if these conditions are satisfied. This is just the sufficient conditions for a. Now, actually, we left off earlier. I imposed another condition, fyy greater than 0. But that is implicit in this condition, because if fxx is positive, then the only way this could be greater than this is if fyy were positive too. Because if fyy were negative or 0, this wouldn't be greater than that. So this was really redundant. It's implied by this. Now, the condition for a maximum is that the second order total differential be negative definite. That no matter, for all possible values of dx and dy, that the second order total differential be negative. See, then you're at the top of a hill. When you're at the very top of the hill, dz is 0. But suppose you travel away from the top of the hill. Then dz is becoming negative. So you're going from 0 to negative. That's a negative rate of change. That means the second order total differential is negative for all possible values of dx and dy. So the sufficient condition for a maximum is just this. Change this f sub xx. Change this a, in other words, to be negative. But you still need AB to be greater than H squared. And by the way, if this is negative, that implies f sub y has to be negative t. Because otherwise this condition right here couldn't hold. Okay. So that's where these second order sufficient conditions come from. And it's extremely brilliant mathematics to figure this out, because there are really infinite number of paths you could take. You have to figure out that the second order total differential is negative for all possible values of dx and dy. Okay, that's where the second order sufficient conditions come from. Okay. You know, actually, I'm not used to teaching in the afternoon. Actually, we're supposed to go for 2.5 hours. So I have you actually for another 15 minutes, because we didn't start till 1. Okay, so we actually have some more time. I saw Gene come in and I thought, oh, it must be nearly time to finish. We got another
I tried, guys.
She tried. Tried to get you out of class a half hour early. Okay, let me give you some economic examples. The first example, I'll follow Chang, and we'll go over the case where you have a two-product firm. I can find the notes here. Yes, okay, here we go. The firm, let's say, produces two products, product 1, product 2. And Q1 is the quantity produced of product 1. Q2 represents the quantity produced of product 2. The prices are P1 and P2. And let's assume this firm has the following cost function. Total costs are just a Q1 squared plus a Q1, Q2 plus Q2 squared. Simple cost function. Depends on how much of product 1 you produce, how much of product 2 you produce. And to keep things simple, let's assume that this firm sells its products in competitive markets where the prices are determined by supply and demand. So the price of product 1 is 100. The price of product 2 is 80. So the firm can sell as much of product 1 as it likes at $100 a piece. The firm can sell as many units of product 2 as it likes at $80 a piece. There's your cost function. The question is, assuming that the firm wants to maximize profit, how much of product 1 and product 2 should it produce and sell? How would you go about figuring out the answer to that? We want to find Q1 star and Q2 star. Zach, were you saying something?
I was just going to say that. I thought it was not a rhetorical question.
Oh. Okay.
Should we start with the revenue?
Okay. What would the firm's revenue function be? Yeah, that's a good start, good suggestion. What would revenue be? Total revenue. It's a little bit different because now the firm produces two products, not just one product as before. Now the firm produces two products. So what would revenue be? Josh? Great, okay. It would be the revenue from selling the product 1, which would be P1, Q1, plus the revenue from selling product 2, which is P2, Q2. And it simplifies a little bit more, doesn't it, Josh? Because What do we know about P1 and P2? You gotta speak up. I'm getting on in years, and so I don't hear very well. You're right, you do substituting. P1 is fixed at 100. So it's just 100 Q1 plus 80 Q2. Okay. Now we're assuming this firm can sell as much as they want. It sells in competitive markets. As much as they like a product one at $100 a piece. As many units as they like product two, they sell at $80 a piece. So the revenue function is very simple. Okay. So that's good. We've got the revenue function. What next?
Set that equal to the cost function?
Oh, okay, wait. Let's assume that we want to make as much money as possible. So actually, you should be thinking about what is our
Objective function.
objective function.
Profit,
Profit. Right. And what is profit?
revenue minus cost.
Exactly. Revenue minus cost.
Did you say revenue, set it revenue equal to cost?
Profit would, by definition, is revenue minus cost. Now, we have both revenue and cost expressed as functions of Q1 and Q2, don't we? All we have to do is substitute in. And we get our profit expressed as a function of Q1 and Q2. Notice there are two variables here, not one. The revenue is just 100 Q1 plus 80 Q2. Minus cost, which is just given to you. That's our Q1 squared plus Q1 Q2 plus Q2 squared. Okay. Or, well, we could simplify just a tiny bit. It's 100 Q1 plus 80 Q2 minus Q1 squared minus Q1 Q2 minus Q2 squared. There we go. We can't simplify it anymore. That's good. Okay, this is our objective function. Whenever you're trying to maximize or minimize something, the first step is to get your objective function, the thing you're trying to maximize in this case. Okay, what next?
Take the partial with respect to.
Yeah,
Yeah.
exactly.
Okay.
Take the partial derivative of profit.
Respect to Q1 and respect to Q2 except by equal to zero.
Exactly. I knew what you were going to say. Yeah, okay.
Place it now then instead of freaking out.
Okay, so pi sub, let's use this notation. Pi sub 1 is just partial pi, partial Q1. Okay, so it's this kind of simpler notation, pi sub 1. And that is going to be what, Zach?
100
Right,
minus Q2.
minus,
Q2. Q sub 2.
okay. I think there's another one
Minus
before that.
Q2.
Yeah, minus 2Q1.
Yeah.
Don't want to forget that one. Minus Q2. Okay, I think that's it. And what do we do with that?